In this lecture, we shall continue with our discussion on continuous maps. So we begin by proving that some familiar maps are continuous. So theorem, consider R comma R2 with the standard topology then the following maps are continuous. The first one is the addition map given by the tuple x comma y is being sent to x plus y. And the second one is the multiplication map, which is given by x comma y maps to x y. So proof. So recall the lemma we proved in the previous lecture. So the lemmas are the following. Let f from x to y be a map of sets. So x and y are topological spaces, and let P be a basis for the topology on Y. So if f inverse B is open in X for all V in this basis, then f is continuous. So we will use this lemma to prove the theorem. So let us consider the first assertion. So let x comma y be in R2, and recall that we are used this notation as epsilon x comma y. There's those pairs x prime y prime and R2 such that the absolute value of x minus x prime is less than epsilon, and the absolute value of y minus y prime is also less than epsilon. So we make an observation first. If x prime and y prime are in S epsilon x comma y, then the absolute value of x prime plus y prime minus x plus y is less than equal to absolute value of x minus x prime plus absolute value of y minus y prime, which is strictly less than 2 epsilon. So this implies that absolute value, so just rewriting this statement, a of x prime comma y prime minus a of x comma y is strictly less than 2 epsilon. So this implies we have proved. So this shows that S epsilon by 2 of x comma y is contained in A inverse B epsilon of x plus y. So using this, so using this observation, we shall show that the addition map is continuous. So let B epsilon z contained in R be a basic open set. So suppose x comma y belong to A inverse of B epsilon z. So this implies that x plus y belongs to B epsilon z. This implies there exists epsilon prime which is positive such that B epsilon prime of x plus y is contained in B epsilon z. So from the above computation, or observation, it follows that S epsilon prime by 2 of x comma y is contained in A inverse of B epsilon prime of x plus y, which is contained in A inverse of B epsilon z. So what we have proved. Yeah, so we have proved that for every x comma y in A inverse B epsilon z, there is an epsilon prime positive such that S epsilon prime, let me say epsilon prime prime of x comma y is completely contained in A inverse B epsilon z. So this implies that A inverse of B epsilon z is open. Thus, A is continuous. So let us now look at the second assertion, the proof of which is similar. So we will show that M inverse of B epsilon z is open. So once again, we make an observation first. So let delta be any real number between 0 and 1, and suppose that x prime comma y prime belongs to S delta x comma y. So then absolute value of x prime y prime minus xy is equal to x prime y prime minus xy prime plus xy prime minus xy. This is less than equal to absolute value of x prime minus x times absolute value of y prime plus absolute value of x times absolute value of y prime minus y. Now absolute value of y minus y prime is strictly less than delta. So this implies that absolute value of y prime is strictly less than absolute value of y plus delta. And since delta is less than 1, it is strictly less than absolute value of x minus x prime. And this is strictly less than delta into mod x plus mod y plus 1. So this computation shows that the image of S delta xy is contained in the ball of delta S of xy. So we let epsilon be between 0 and 1, then epsilon by mod x plus mod y plus 1 defined to be delta prime is strictly less than 1. So thus we have proved. So thus we have proved. Okay, so not delta prime, just delta. So if we take this to be delta, we have proved. So by substituting this value of delta, that for any epsilon between 0 and 1 and x comma y in R2, this open set x comma y is contained in M inverse of P epsilon xy. So suppose, so now we will use this to prove that the map M is continuous. So suppose x comma y is contained in M inverse P epsilon z. Then there is an epsilon prime positive such that P epsilon prime is positive and is strictly less than 1 is contained in P epsilon z. So let me say so from the above computation, it follows that S of epsilon prime by mod x plus mod y plus 1 of x comma y is contained in M inverse of P epsilon prime xy, which is contained in M inverse of P epsilon z. So this proves that M inverse P epsilon z is open, and so M is continuous. So, similar to this theorem, let us prove another result. So this completes the proof of the above theorem. And let's also prove this result. So let r star equal to r minus 0 with the subspace topology. Now let f from r star to r star be the map x goes to x inverse. So this map is continuous. So proof. So let x be in r star. So one checks easily that if epsilon, so we look at the collection of sets, the collection B epsilon x. Okay, so one checks easily that if epsilon is strictly less than mod x, then B epsilon x is properly contained in R star, and that sets of this type form a basis for the subspace topology on R star. Thus, thus it is enough to check that f inverse P epsilon x is open in R star, where epsilon is strictly less than x. So the picture looks like this. This is 0. Let's say x is here, and this is x minus epsilon, x plus epsilon. Now it is easily checked. F inverse is equal to 1 upon x plus epsilon, comma 1 upon x minus epsilon, which is open. So this proves that f is continuous. So these were three very concrete maps between spaces which we are familiar with. We have seen these maps a lot of times, and we just now proved that these maps are continuous. So let's keep this in the background now, and we return. So we return to proving some general properties of continuous maps. So lemma, let x, y, and z be topological spaces And suppose we have maps F and G such that F and G are continuous. Then the composite map G compose F is from X to S, X to Z is also continuous. And the proof of this is left as an exercise. The proof is very easy. Just uses the definition of continuity. So here is another lemma, another easy lemma. Let F from X to Z be a continuous map. And let Y be a subspace of X, and let I denote the inclusion from Y to X. Or subset. So this Y, subset Y, we give it the subspace topology. The subspace topology. Then the composite F compose I is also sometimes referred to as the restriction of F to Z is continuous. So proof. So recall that the inclusion map is continuous when Y has the subspace topology. Right, and from the previous lemma, the composite of continuous maps is continuous. So this implies that F compose I is continuous. So let F from X to Z be a continuous map. And suppose that the image F of X is contained in a subset Y of Z. That is, F of X is contained in Y, and that's a subset of Z. So let I from Y to Z denote the inclusion. So this means that the map F factors as follows. So this map we should denote F naught. So the map F naught is simply X maps to F of X. But now we view F of X as a point in Y. So this lemma states the following. So let the notation be as above. If y is given, the subspace topology, so this map is I, then f naught is continuous. So let us prove this. So proof. So let U containing Z be open. Then I inverse U is equal to U intersection Y is open in Y. So all open subsets of Y have this description. Thus, to show that f naught is continuous, it suffices to show that for every U open in Z, we have f naught inverse of I inverse of U is open in X. So, but f naught inverse of I inverse of U is exactly equal to f inverse of U, as f is equal to I compose f naught. As f is continuous, this set is open. So this shows that f naught is continuous. So we will use this result soon. So let us prove this proposition. So let X be a topological space and let yi for I in I be a collection of topological spaces. So suppose we are given a collection of maps fi's from X to yi. Then we can get, so all this is at the level of sets, a map capital F from X to the product of yi's, which is simply defined by sending X to the tuple fi of X for I in I. So the statement of the proposition is that f is continuous only if all the fi's are continuous. So proof. So first let us remark that the product, as we had mentioned, is given the product topology. So first, let us assume that f is continuous. So we know that the projection maps Pj from product I in I, yi to yj are continuous. So this shows that the composition so x product, here we have f, here we have pj, is continuous. But the composition is exactly equal to small fj. So this implies that, and this happens for all j, fj is continuous. So thus all the fj's are continuous. So this proves one direction. For the second direction, the conversely, assume that all the fj's, all the fi's are continuous. So recall the product topology has as basis sets of the type product I in I ui, where all but finitely many uj are equal to yj. So these sets form basic open sets, and thus it suffices to show that if inverse of these sets, of any one of these sets, is open. But now it is a trivial check that f inverse of this product is equal to intersection I in I fi inverse of us. So only finitely many of these ui's are not equal to yj's. So only finitely many of these uj's are not equal to yj's. So if ui1 up to uin are the sets which are not equal to yi1 up to yin, then the above intersection so whenever j is not equal to any of these I1 up to In, then this uj is equal to yj, and fi inverse of yj is all of xj. So this piece is just going to be x. You solve x, sorry, not xj. So we have intersection I in I, f I inverse of ui. So this we can write as intersection I, let's say j in I1 up to in fi inverse fj inverse of uj intersected with j not in I1 up to in fj inverse of uj. But this, each of this is equal to x, so this just becomes equal to in fj inverse of uj. But now each fj is continuous, and so fj inverse of uj is open in x. Since a finite intersection of open sets is open, so it follows that f inverse of intersection, f inverse of the product ui is open in x. This implies that f is continuous. So this completes the proof of the proposition. So as a consequence of the above proposition, we have the following. So let f comma g from x to r be continuous maps. So then we have maps f plus g and fg defined as follows. These maps are defined even when f and g are not continuous. So f plus g at the point x is equal to f of x plus, so let me write on ui. So f plus g of x is defined to be f of x plus g of x, and fg of x is defined to be f of x times g of x. So the claim of the proposition is both these are continuous. So the proof is easy, and it combines what we have proved so far. So we consider the map x to R2 f given by x maps to the tuple f of x comma g of x. So this map is continuous by the preceding proposition, as both f and g are continuous. Now then the map f plus g is simply equal to a compose f, and fg is equal to m compose f, where a and m are the addition and multiplication maps from R2 to R. So here we have f. So a is composition. This is the addition map. So a compose f will be f plus g. And similarly, we have already seen that the multiplication and addition maps are continuous. So therefore, this composite is fg. So as a composite of continuous maps is continuous, the proposition follows. So similarly, we can prove one more result. That f comma g be from x to r be continuous maps such that g of x is in R star for all x in x. Then the map f by g from x to r, defined as f by g of x, f of x by g of x. So this new map is continuous. So how do we prove this? So as g of x is contained in R star, using our earlier lemma or our earlier result, it follows that when we look at the map G from X to R star, so G actually defines a map from X to R star. This map is continuous with R star having the subspace topology. So now consider the map R cross R star to R given by x comma y maps to xy inverse. So this map can be written as a composite R cross R star to R cross R star to R x comma y gets maps to x comma y inverse. This gets maps to xy inverse. So the second map, this map, is a restriction of the multiplication map. Okay, so let me just write this as M. This map M from R plus R. Okay, so let me not write this. So the composite is just x comma y goes to xy inverse. Now note, so note that the product topology on R cross R star is the same as the subspace topology from R cross R. So, so now we can check. So the first map, so easy exercise. So we're using the above results. Check that the map R plus R star to R plus R star given by x comma y goes to xy inverse. X comma y inverse is continuous. So the multiplication map is continuous and this map is continuous. The first map is continuous. So this will imply that. So both maps are continuous. And so they are composite is continuous. So now consider the composite. So this proves, so this shows that the map from R cross R star to R given by x comma y maps to xy inverse is continuous. Now consider the composite. Given by x maps to f of x comma g of x. This along with the above map. So then this will get sent to f of x by g of x. So thus the composite map. The first map is continuous because f and g are continuous. So this map is continuous as f and g are continuous. So therefore, the composite is continuous. So this proves the proposition. So we make a remark. These results prove that collection of continuous real valued functions. So this collection is closed. Continuous real valued functions on a topological space is closed under some of the natural operations. So we will end this lecture here.